Hello everybody! Welcome to Miscellaneous Tidbits. Today we're talking about business calculus. Business calc is a class that claims to be about teaching practical calculus from the perspective of economics and business. But math classes like this are super idealized and they don't really represent how complicated the world actually is. So today I would like to show you some things that you will see in the real world. And I'm going to show you how to use Microsoft Excel or Google Sheets to solve real-world calculus problems that will come up for business majors. The specific uses that we will highlight today: loans, populations, economics, and brewing. So before we proceed, I'm going to assume that you know what a derivative is. If you don't, that's okay. I have a whole Secrets of Calculus series that will give you a nice crash course into how the derivative works and what it does. So what I'm going to introduce today is known in math as a differential equation. That sounds scary, so the name is often shortened to diffie-q, or my personal favorite, diffie-q. So what is a diffie-q? A differential equation is an equation involving functions and their derivatives. So let's say you had some function y of t. Oftentimes, we name the function the same as the output variable, because otherwise things would start getting confusing pretty quickly. So this function inputs numbers t and spits out numbers y. A diffie-q could be something like y prime of t equals y of t, which is often written as y prime equals y. Now, if you were tasked to solve a diffie-q, your task would be to find all the functions y of t which make this equation work. So essentially the question is, what functions have the derivative equal itself? Now if your answer is e to the t, you've got the right idea. But here's a question: is that the only solution? As it turns out, no. You can also do y equals 2e to the t, 3e to the t, negative e to the t, and also y equals 0 works. So in general, y equals any constant times e to the t will make this equation true. Now once you solve a differential equation, the result is also going to be a function. And that tells you that given some input, you get this output according to whatever the function says to do. So as a reminder, the derivative gives you the change in the output at some input. So why would we use a differential equation? Why couldn't I just tell you to work with e to the t? Well, it's because the world is complicated. Sometimes, most of the time actually, you won't have exact solutions to things, and you won't have nice input-output functions. But what a differential equation says is that the change in a thing has something to do with its current state. That is a lot of information. And in this first case, it is literally saying, whatever your current output is, that's how much your output will change. And that is powerful. So let's look at an example that's probably very relatable, especially if you live in the United States. Consider student loans. Student loans, and any loans for that matter, follow the rules of compound interest. So they will have a percentage rate. This year the federal interest rate is around 6.5%. But now this time, I'm not just going to write a bunch of letters and expect you to memorize what they mean. Let's instead construct a differential equation. So our rate is 6.5%, so that means each time we measure the amount that we owe, it will increase by a factor of 0.065. So that means the change in what we owe, let's call that a prime of t, that will equal 0.065 times what we currently owe, which we'll call a of t. So a prime equals 0.065 times a. We're not going to directly solve this equation, though if you do, you'll actually get the classic formula for continuously compounding interest. So that's pretty cool. But we're not going to do that. Instead, we're going to plot a bunch of points, and we're going to approximate the solution. So this is where we jump into Excel. So if you're following along with me, you'll want to create 3 columns. The input t, this will be the time in years since you took out the loan. We'll have the output a, the amount that you currently owe on the loan. And we'll have the derivative a prime, which is how much your loan will grow each year. So in the input column, we put the number of months going 0 to, I don't know, a lot. Student loans are expensive. It might take a while to pay these off. At time 0, that's when we actually take out the loan. So let's say the loan is $50,000. So you'll be putting $50,000 in this first cell for the output. Now what's the change in that output going to be? That's where we refer to our differential equation. A prime here is 0.065 times the output cell here. So we can drag that formula all the way down the column because it's going to stay the same. Now how do we update our outputs based on this derivative information? Well, let's think back to what a derivative is. Given some input, the derivative will tell you the slope of the tangent line at that point. We don't know exactly what this function is doing, but this tangent line is going to give us a pretty decent approximation. So if we want to figure out how far we need to move along this line, we have change in A is going to equal the slope times the change in the input. And we know what the slope is. That is what the derivative tells us, and the derivative is right there in that third column. And we also have a change in input. You just go over to this column, subtract this cell from that cell, and this is a change in output, so we'll want to add this result to the previous output. And that gives us our new approximate output. So notice how we never had to figure out what function this actually was. And yet, when we drag this formula all the way down, we can get an idea of what happens to the amount that we owe. And if we plot this on a graph like this, the amount that we owe will be growing exponentially, which is exactly what we expect to see in our compound interest formula. But you see, the world is complicated. When you take out a loan, you're expected to pay it off. So let's put a cell here that says how much we'll pay each month. Put maybe $100 here for now. We'll freeze the top row so that we can see this number. And let's say that you graduate in 4 years and you get a job that lets you start paying off the loan right away. So that means at month 48, your differential equation will start changing. Instead of just constantly adding interest, you're now removing $100 each month. You'll want to lock the targeting of this cell because we'll be changing it and seeing what happens. And if we drag that new diffq all the way down, we see that the behavior will change. Again, we don't know what the actual function is. In case you're curious, here's what Wolfram Alpha spits out. And this is exactly why I'm showing you the Excel method, because things can get pretty gnarly pretty quickly. But we can approximate this pretty well, and we can at least get an idea of what we're looking at. And here we can see that $100 is not quite enough to be able to pay off the loan. It's still going to be exponentially growing. So what will make it start shrinking? We need the derivative here to be negative. And so by our diffq, we need the amount we pay off to be greater than the amount that gets added on. So let's adjust this cell, and this gets us a 0 derivative. So that means the loan stays the same. And then if we increase the payoff just a little bit more, well, check it out now. Now we're decreasing. In fact, it looks like if we continue paying the exact same amount, the loan will start shrinking exponentially. Now let's go one step further. We'll make a column here for how much we pay off, and after month 48, we'll just copy the same number all the way down. We'll also copy the diffq all the way up as well. And lastly, we'll add an if statement to the output, where if the number you're about to get is negative, we make it 0. So now we have a column where we can play with how much we pay off each month. So we can start by paying maybe $50 per month while we're in college. And that, check it out, that saves a ton with paying off the loan later. And then after we graduate, maybe we get a promotion after a year, so we ramp up the payments towards the loan. And now we can estimate how long it takes to pay off the student loans, and we can adjust the differential equation as we go to reflect what we actually do. How cool is that? So there you go. Now you know how to use calculus to not only measure how much your loans are messing with you, but also figure out how much you have to pay per month in order to beat the compound interest, and also what will happen when you do that. So next up, let's look at population dynamics, also exponential. Let's say you run a fish meat business. If you want to stay profitable long term, and also in order to just not be an absolute jerk, you'll want to make sure you don't accidentally harvest the fish to extinction. So a classic population growth differential equation looks like this. Here we have a rate of growth, and then we also have a carrying capacity, which is the maximum number of fish that can reasonably be able to live off this whatever this patch of water is. So let's plug that into our Excel sheet. And for now, we won't be going in and harvesting the fish. Notice how the population starts off growing exponentially, but then it tapers off as it reaches the carrying capacity. So when we go to harvest the population will be quick to recover. But if you harvest too much and too often, you risk extinction. And this is why exponential demand is a terrible thing. It only works if your product can increase in amount exponentially forever. And as you can see here, populations don't do that. If you start exponentially increasing how much you harvest, you'll very quickly run yourself out of business. So real quick, back to theory. What I'm going to demonstrate is a use for critical numbers and also limits going to infinity. So a DiviQ has an equilibrium if the solutions to it have a horizontal asymptote. Here with the population DiviQ, we saw that the carrying capacity was a horizontal asymptote. And notice how as you get closer to the asymptote, the slope starts flattening out, or the derivative approaches zero. So that means we can find these equilibria by setting the derivative equal to zero and solving for the population that makes this happen. Solving for p here. And if we do that, we get solutions at p equals 0 and also at our carrying capacity. So these will be our equilibria. We can then classify these things the same way that we classify critical points. You place your equilibria on a number line. These are the only places where the derivative is 0. Now you can sample points near the equilibria and figure out if these populations make the derivative positive or negative. We've seen this idea to show that a critical number is a relative or local minimum or maximum, but now we just change the names. If we have this situation, it's called a stable equilibrium. The idea is that if you're going along and you get knocked off course, you'll be pushed back to the equilibrium. In this situation, it's called an unstable equilibrium. The idea is that if you get knocked off course, you'll be pushed away from that point. And then if you have something like this or like this, these are called semi-stable equilibrium. So let's do another example where we can see this kind of thing in practice. Supply and demand usually have a linear relationship with price. Price goes up, supply goes up, but demand goes down. It's a classic problem in economics to find this sort of equilibrium point. And yes, that's the same name we gave to important features of our DiffyQ. There's a good reason for that. Because when you first start your business and you're searching for that equilibrium, the prices are going to be changing over time. And that's where we see our price differential equation right here. Once again, we can plug this into Excel and see how the price is going to behave over time. And what we notice is that as time proceeds to infinity, the price will stabilize at this point here. That point is both the supply-demand equilibrium that we were looking for, and it is an equilibrium of our DiffyQ. And that is not a coincidence at all. The economic equilibrium was actually defined with the DiffyQ in the first place. And then if you want to analyze this equilibrium, you'll see that it is stable. So regardless of where the prices start, you'll be pushed towards this equilibrium point. Now there's two different ways to expand on the DiffyQs that we've been talking about. The first way is to change how many derivatives we take. All of these previous examples are called first-order DiffyQs because they only use one derivative. But sometimes the acceleration in a thing will depend on current speed and position. Anytime we have acceleration, we are working with the second derivative. And then we can create what's called a second-order differential equation. So here's an example. We're going to look at supply, price, and expected rate of inflation. They're going to be related by these equations here. So right now, this looks like a bit of a mess, and it is. So let's say we're interested in figuring out how the price will change over time. So to do that, we're going to take the derivative of the price function, and we're going to plug in what we know. And here we can plug in I prime of t, and we can use the price equation to solve for inflation, which gets this. So now, how do we deal with this sort of thing in Excel? Well, now we need another column for the second derivative. And that second derivative is going to depend on current output and the first derivative. Now, if we want to approximate the first derivative, we can use a standard setup. After all, the second derivative is nothing more than just the derivative of p prime. So we can use all the same derivative things, just standard things here. But now what about the output? We can do what's called a quadratic approximation, which looks like this. And there we go. Now we can see how the solution behaves over time. And we can also tweak these numbers to see how things behave. So for example, this constant in the inflation diffeq can drastically change how the prices behave. If it is small, the prices will stabilize, but if it is large, the prices can go crazy. And by the way, a diffeq can have whatever order you want. Each time you add a new order, your approximation will add a 1 over n factorial times the nth derivative of y times your change in output to the power of n. In fact, even if you're approximating an equation and you're not approximating a diffeq, this method is used quite frequently to get better estimates. And in fact, if you keep adding on these estimates to infinity, you'll get back the original function. So, cool little math fact for you. A second way to expand on the diffeqs we've been talking about is to chain them together into systems of differential equations. So a common use of this is brewing beer or other alcohol. In the brewing process, there is a step where the concentration of alcohol in whatever your water or liquid solution is controlled and then stabilized, and that is done by dumping your solution in a tank of water, letting it mix, and then pouring the result out of the tank. So let's look at an example problem. Let's say we have a 100-gallon tank which is full of water, and let's say it has 10% alcohol in it. We're going to pour solution in at a rate of 50 gallons per minute with a solution that is 50% alcohol. We will then drain the tank at a rate of 50 gallons per minute. So what we want to know, after we switch on these valves, what's the concentration of alcohol going to be in the tank? And this is the job of a differential equation. So the amount of alcohol will change according to the input minus the output. We input 50 gallons per minute with 50% concentration, so that means we're pouring in 25 gallons per minute of alcohol. We then output 50 gallons per minute with, well, we don't actually know what the concentration is going to be. It's going to change over time. It's whatever the current concentration in the tank is. But what we do know is that concentration is amount divided by the volume. Our tank has 100 gallons in it, so the concentration is going to be whatever the current amount is divided by 100. And so that is the percentage of alcohol in the liquid coming out of this tank. So now we can approximate the solution using our usual Excel spreadsheet, and that will tell us the amount of alcohol that is present at any given moment in time. So now if we want concentration over time, we can take this output and divide by 100, and we can see how this concentration will stabilize over time to be 50% alcohol, just like the input. And that's to be expected. But that also means that we can adjust the valves to get whatever concentration we want. So now let's do a more complicated brewing setup. Rather than just pouring in and pouring out, we're going to pour from one tank into another tank and then pour out of the second tank. So in the first tank, we're going to pour in at a rate of 10 gallons per minute with 10% alcohol concentration. Tank 1 holds 50 gallons and starts with a concentration of 0% alcohol. We're then going to pour that result into tank 2 at a rate of 15 gallons per minute. Tank 2 holds 100 gallons and starts with a concentration of 90% alcohol. We're then going to pour that result of tank 2 back into tank 1 at a rate of 5 gallons per minute. And we're also going to pour stuff out of tank 2 at a rate of 10 gallons per minute. Notice here, all the numbers balance out so that neither tank will lose or gain any liquid. That's what we want if we're trying to brew things long term. So to analyze this situation, we're going to make two different differential equations. One to describe the amount of alcohol in tank 1, the other for tank 2. Both will use that input minus output idea to construct it. So for tank 1, we input 10 gallons per minute with 10% concentration. And then from tank 2, we input 5 gallons per minute with whatever tank 2's concentration is. Now we output 15 gallons per minute from tank 1 with whatever tank 1's concentration is. And so we subtract that. And then for tank 2, we input 15 gallons per minute with whatever tank 1's concentration is. And then we output 5 gallons per minute and 10 gallons per minute from two different places, but they're going to have the same concentration. That being whatever tank 2's concentration is. So what we have here is two different diffeqs which are linked together and that depend on each other. So what we're going to do is we're going to plot both on the same Excel graph. We'll just need to create another column for the second output and the second output's derivative. And so here you can see we have two graphs going simultaneously and both will stabilize to their own concentrations. This is an extremely common thing to see, and in fact, the way that computers often solve higher order diffie-qs is by turning them into systems of first order diffie-qs, because that's more efficient for the computer, for reasons that I don't fully understand. So there you go, differential equations. They run the world, you'll probably be working with them all the time, and you will probably never be taught anything about them in a business calculus class. Which is a real shame, because yes, it is important to know product rule and other derivative rules. After all, we saw that in that second order example that we did. But it's also important to know how to approximate solutions in Excel or other program, because the world is complicated. You'll likely never to see nice functions anywhere, but you are likely to see nice relationships between quantities and their changes. I hope you enjoyed this video, and I hope it helps you see why people care about all the stuff that you've learned in business calculus. And I'll see you later.